I think it's 8:30. Let us formally start. I'd like to welcome you all in this Saturday manufacturing, the talks. And the Saturday manufacturing talk is getting organized by the Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur. The Center of Excellence has been set up with this, the support from the Ministry of Heavy Industries and Public Enterprises and a consortium of industries where the presence of public sector and the private sector. We are doing research on various, the verticals like materials, the design and automation, additive manufacturing, and industry 4.0. Now, our, the talks we started, in the month of March, and today is the 16th week. We are having speakers from different fields of the manufacturing, and today's talk is on the system health, the management, which is an important topic as far as the, intelligent systems is concerned. So we all know that for any automation, if you would like to make a system intelligent, then we'll be constantly gathering data from the system, and then how to analyze it and how to develop, the models, which will include both the data model, the data, and also the physics-based model, simulation-based model, and how to, they come up with the prescriptive models for the preventive maintenance. So today's speaker is Professor Krishna Pattipati. So he will talk about all these aspects. He'll also give us some, some of the case studies or the applications in the automotive, aerospace, power systems, buildings, and medical fields. So let me, read the brief, the biosketch of Professor Pattipati. Professor Krishna Pattipati received his BTech degree in electrical engineering with highest honors from the Indian Institute of Technology, Kharagpur in 1975, and MS and PhD degrees in system engineering from University of Connecticut in 1977 and 1980 respectively. He was with Alpha Tech, Massachusetts from 1980 to 86. He has been with the Department of Electrical and Computer Engineering since 1986, where he is currently the Board of Trustees Distinguished Professor and the UTC Chair Professor of System Engineering. His research interests are in the application of the system theory, optimization, and inference techniques to agile planning, anomaly detection, diagnostics, and prognosis. He has published over 500 scholarly journal and conference papers in these areas. He is the co-founder of Qualtech Systems, a firm specializing in advanced integrated diagnostic software tools, and serves on the board of Aptima. Dr. Pattipati was selected by the IEEE Systems Man and Cybernetics Society as the Outstanding Young Engineer of 1984 and received the Centennial Key to the Future Award. He has served as the Editor-in-Chief of the IEEE Transactions of System Man and Cybernetics Part B from 1998 to 2001. He is an elected fellow of IEEE. With this brief, the reading of the biosketch of Professor Pattipati, I request him to start his, the talk. We are all eagerly waiting for that. Professor.
Great. Can you see it?
Yeah, it's fine. Yeah.
Okay. Professor Paul asked me to talk about system health management. We developed something called multifunctional models. These are causal graphical models in the late 80s for system health management. And these are now part of a commercial toolset called Teams for integrated diagnostics and prognostics. About a third of my PhD students worked in this area. And I would like to single out Somnath Deb, who happens to be Chief Technology Officer and the President of QSI. And he also happens to be a graduate of IIT Kharagpur. In fact, I strongly recommend that maybe you get him to talk at one of your sessions because he's considered a thought leader in this particular area. So in fact, has a lot more practical experience than I have. And the CEO of this company also happens to be a IIT Kharagpur person. That's Dr. Sudipta Ghoshal. So I'm not graduated in 87 from the ECE branch. Sudipta was, like me, was an EE graduate from 89, and I'm a 1975 graduate. So before I start my talk, let me briefly say a couple of things about IIT and why I think great about IIT Kharagpur. I feel that I got the best education there, mostly with merit scholarships. And for those of you that are going to IIT now, my parents had to pay only about 150 rupees, which is $20 those days, in 1975 dollars. It used to be 7.5 rupees for $1. So I got very good education, pretty cheap. And E at that time had the best teachers, I believe. Professor K.B. Menon, who taught me power systems, and everybody feared him, but he was very kind to me. And Professor N.K. Shomurthy he taught me signals and systems. And in all the talks that I gave, I say that he was the best teacher ever for me. And he inculcated my interest in systems theory. And in fact, he visited me in Boston. And what I found, the teachers they were very tough in class, but very nice people outside. He visited me and my wife in Boston when I was working for Alpha Tech in 1983, and we had a great time with him and his wife. Professor Balram Murthy, who taught me machines, and in fact, he became a family friend when he started working at General Motors R&D. And there were lots of other professors that taught me great things, like Professor Venkatatnam, who taught me electromagnetics waves. I do remember a number of other professors, Y.P. Singh, he taught me controls. Professor D.V.S. Murthy, Professor Chattopadhyay, Professor M.K. Ghosh was my thesis advisor, by the way, and Kanti Prasad Rao and Professor Padmanabhan. So quite a few great teachers. And the last mechanical engineering course I remember having was a strength of materials course. So I was not very good in mechanical, by the way. So I was from Patel Hall, for those of you, I don't know how many of you are from Patel. And I feel that this Saturday night is an appropriate time because, as I remember, that is the only day we used to get good food at Patel. So with that, let me go into what the system health management research that we've been doing in CyberLab. CyberLab has been started somewhere in 1976 with my advisor, who's David Kleinman, who's very well known in optimal control. And what we feel is that this graphical model that we have developed are a nice integrating mechanism for integrating physics-based, machine learning-based, or the data-driven type models, and even domain knowledge or the expertise that people have about machines and about any systems that they know about. That's because you can actually bring in not only the physics, the data, the real life, and also rules of thumb can be brought into these kind of graphical models. My lab essentially focuses on the use of systems theory, optimization, and probabilistic inference to solve problems of interest to commercial, industry, and national defense. 80% of my research nowadays is on mission planning, primarily for the US Navy. And a lot of the work that we have done in integrated diagnostics and prognostics, now we're applying them to automotives, for example, power modules and automotive systems for especially Toyota, and resilient habitats, the mission to Mars and the moon. And the company that I started with, the Qualtech, they're involved in this mission to the moon, so-called Artemis program, and they're also applying it to Navy boats and also a manufacturing facility at the Warner Robins Logistics Center. So this whole area, so why I think that this is a nice integrating mechanism. For example, if you have got a data-driven, just only data, you can actually build classifiers that distinguish among the different anomalies or different faults. And that is what is called the error correcting code matrix, or we call it the diagnostic matrix, or the so-called D matrix. And as you know, a matrix is essentially a bipartite graph. You can think of rows as one set of nodes and columns as another set of nodes. So it's essentially graphical models can be incorporated into that. And of course, you can take the data and do system identification and develop models and then use them for whatever predictive purposes that you want to use. Or they could also be purely physics-based. And now those are becoming quite popular because with the GPUs, you can actually run fairly complicated physics-based models. And you can do false simulations on those to get that same diagnostic matrix. And as I'm going to illustrate to you that you can actually use non-traditional measurements into these kind of graphical models. So this research has been actually a fascinating journey for me. I was introduced to this topic by Joe Wall, who was VP at AlphaTech, which is actually a MIT offshoot company that was started in '79. And Joe happened to work in the Apollo program, especially on the troubleshooting. So when he introduced me to this problem, he said, hey, can you come up with better algorithms? So what I did was I set it up as a markup decision problem, and you could use dynamic programming. But dynamic programming doesn't scale up because of the curse of dimensionality. Question is, can I get some cost to go estimates? And I was able to get it using some information theoretic concepts of coding. And that actually won the best paper award at one of these test conferences. And that led to this whole research in system health management. In 1986 and 87 timeframe, and Somnath came. By the way, Somnath's PhD was not in the system health management. He worked more on the multi-target tracking problems. But after he took a course with me on linear programming network flows, he said, hey, why the traditional ways of doing it using this text type representations of dependencies, I can represent it as a graph and then use reachability analysis to find this so-called diagnostic matrix. And that led to the research with some helicopter companies like Sikorsky and Boeing, and also NASA. NASA got interested in that, and so they funded a lot of this work over the next 15 years or so. And then in '93, one of the engineers from Sikorsky said that, hey, we need to have this software maintained and so that we can actually use it on the real systems. And that's when we started this Qualtech Systems, and which Somnath is leading right now. And that led to a whole set of other tools. On the space station, we use a so-called remote diagnostic server. Way back in the '90s, we developed this maintenance over the network type of things. And also at the same time, we developed real-time diagnostic, onboard diagnostic tools, and a whole set of tool sets were developed over the years. And then we got involved in automotive somewhere in 2002, 2003, both Toyota and General Motors. And then this whole tool set got used on some rocket launches like Ares 1X, and is being used in a lot of medical as well as automotive buildings and engines, all sorts of applications. All right, so nowadays there's a big push for the so-called digital twins and digital threads. So what is it? Why is this made possible? We believe that deep physics-based modeling and simulation, now with all the GPUs, you can actually do some really neat things. And of course, machine learning, especially deep learning enhancements. And of course, virtual and augmented reality, robotics, as Professor Paul mentioned, we have a big facility there. And of course, ubiquitous connectivity, that's basically the IoT, embedded smart sensors, cloud and edge computing. And the nice thing nowadays is that you can actually outsource this domain expertise, as we are doing today. You just called me up a couple of months back and say, can you talk about this particular area? So that's what you can do nowadays. So all those things have essentially made these so-called digital twins possible. And there is a chapter that we just wrote for a book called Digital Twins, and Ken Rosen happens to be vice president of Sikorsky Aircraft. Apparently, he funded a lot of my work in the 80s. I didn't know him that time, but we served on the same committee for on the COVID last year for this Connecticut Academy. And then he said, I want to write this chapter with you. So that's how we wrote this chapter on digital twins. So how does digital twin help in terms of designing? So what we believe is there's a new way of doing the design using something called platform-based design and multiple interacting Vs, which are essentially so-called system Vs that span the entire concept to design to preliminary design, detailed design, manufacturing, operations and maintenance and disposal. You can have multiple Vs interacting. And what is a platform? A platform is essentially a modular design approach that reuses validated and verified subblocks to put together into an overall system. So that way you can actually reduce the time to develop, reduce time to verify, and also shorten the time to market. The key idea of these digital twins is to have a single source of truth representation of your system so that you could collaborate virtually, and you can use it to do three things. A digital twin is sort of like understands what happens in the past through knowledge repositories and legacy data. It has an estimate of the current state, so situational awareness of the current, so the past, present. And also we could use this to predict what could happen given the current situation and make proactive decisions. So digital twins have this application of knowing the past, the current, as well as the future. And what is made possible with this is the techniques such as this multiple Vs, interacting Vs, and also standardized modeling languages such as the SysML and all the tools that you get from these companies like Modelica and MathWorks and things like that. In terms of system health management, as I mentioned in the previous slide, that intelligent systems essentially have these three attributes of health management. They can operate autonomously, and they can predict the future based upon the current status. So how does that impact the system health management? And can you build system health management digital twins? And we believe that those things should be developed starting in the conceptual phase, and that enables you to do a couple of things. You can design your systems for service, and I'll give you some examples of what are the kinds of things that can go wrong if you don't consider those issues of maintenance right at the time of design. And if you have a sufficiently intelligent system, you will know what has happened, and then you can go and you can diagnose before you dispatch maintenance personnel. So quite often what happens is that you call somebody to fix your system, they come and say, oh, look, I don't have this part, or I don't know what's going on, I need to escalate it to the next level. So that essentially increases the downtime, and therefore the system availability goes down. So by having this diagnosed before dispatch, you can reduce this escalation and the downtime, and give you one example of where this is being used in the medical field. So you want to essentially design your health management system into your system early. And that's because of the following thing. This is a view graph that was given to me by a friend of mine from NASA, Mike Battaglia. So if you don't include system health management issues right from the beginning, it impacts supportability of the product, increases the cost of service, and also increases the life cycle cost. So the red curve here is how you have decided on the life cycle cost. And the green curve is actually how you're spending the money over time. So it turns out that by the time you spend only about 5% of the life cycle cost, that's typically in the conceptual preliminary design, you essentially decided on the fate of your product, 85% of the life cycle cost. So if you make wrong decisions at that stage, for example, lack of consideration of system requirements, so people change the requirements of your system all the time, that can have a major impact. Or the ability to be able to evaluate those requirements through models. For example, your requirements can be specified in terms of models, and the teams can use those models to clarify the system requirements. And you can actually simulate the design at the system level right from the beginning, and where you uncover complex system interactions early, and therefore you can fix them early. And it is well known that if you find the problems in the field versus finding the problems in-house, you tend to spend almost exponential amount of time to fix things. And there are lots of cases like that. For example, the example of Boeing 737 MAX. So Boeing lost about almost $15 billion over 2 years because they want to put one simple sensor that will cost them very little. And that caused huge problems for them. And also there was issues with the GM ignition switch recall. It was only going to cost them like maybe $2.50 to $5 per vehicle. And that caused them like maybe $700 million of recall costs. And you know about Takata airbag recall, and Boeing also had another problem with the 787 with their lithium-ion batteries. So what you want to do, in fact, if you look at all the successful designs, you want to spend as much time as you can in the conceptual phase. So how do you do that? By having maybe rival teams doing multiple conceptual designs, and having them share that information and each one critiquing the other teams. And that kind of stuff was actually done for Atlas microscope design at CERN. And that worked out to be extremely well in terms of the life cycle cost and also validation and verification. So what you want to do is you want to catch your problems early, and you don't want to be making errors that are going to escalate from, say, a component to a board level to a subsystem level to the system level, because fixing problems in the field is very expensive. Okay, so now that we know that this is important issue, so how do you build, or how do you go about designing system health management, which I'm going to get to? So the intelligent systems have to have these properties of sense, assess, anticipate, and respond. In order to do that, they need to know what the state is. So the state awareness is the key to system health management. And so there are three terms that you see quite often. One is something called anomaly detection, or that we call them the tests or the error codes. So which is essentially recognizing the deviations of a system from the system's normal behavior. As also people call it the fault detection. The second thing is fault diagnosis, isolating the root cause. And diagnosis involves two things. One is isolation, is basically localizing the faults to physical regions, and identification, which is estimating the severity of the fault. And nowadays, with all this intelligent system, there's also so-called prognosis. That means you want to detect the problems early and keep on monitoring it. And then you want to isolate what could be going wrong and estimate what the remaining useful life is and proactively fix it. So this is what is called the condition-based maintenance, or proactive, or the predictive maintenance. And in fact, Delta Airlines has been very successful in this, where they've used this predictive maintenance to reduce the cancellations due to unscheduled maintenance. And in fact, they've been doing a very good job over the last 5 years. And also a lot of the engine manufacturers have used this kind of ideas, especially with the oil debris monitoring, the helicopters, aircraft, as well as even the petrol boats. So there's an oil monitoring system that can be used to do condition-based maintenance. Okay, so how does this whole intelligent systems become intelligent? Well, you have got to say cyber-physical system. The cyber-physical system is essentially mechatronics plus network with computer systems. And you will have a set of sensors in these systems. And those sensors, we call them the monitored variables. So there is clearly one problem of, hey, where do I place my sensors? So sensor optimization is one problem. Then you want to compare whatever the sensor variables with the nominal values. So how do we do that? Well, you need to have a model of the system. So for example, you could have maybe a consistency checks among the various sensors, maybe based on, say, a physics-based model or a gray box model or even machine learning-based techniques to compare what you expect with what is actually measured. And we call them the residuals or the parity checks or the deltas. And those residuals go through some sort of a classifier, a statistical test, and you get these so-called error codes, the test outcomes, so which could be red, green, yellow, or it could be red and green. So those are the test outcomes. And those test outcomes, you may have multiple of those test outcomes, and those need to be fused together to isolate where the problem is. Those are called the diagnostic decisions. And then you estimate the severity, and then you decide on how do you rectify the problem, and those should be the control actions that go back and control in a feedback loop. So how do I use these models? Well, if you've got a model that involves, it could be physics-based, data-driven, or it could even be knowledge-based models, or it could be a combinations of those, so-called hybrid models that use not only the physics informed by data. And you can, once you have these models, you can use them for designing for service, like, hey, where do I want to, which components I want to replace, at what level, and how often I want to maintain things, how often I want to replace stuff, things like that. All those decisions can be made right at the time of design. And your monitoring mechanisms can be split into onboard, so real-time onboard diagnosis. So the same model can be used for onboard. And then the customer can be maintaining the system. And those that cannot be fixed, the information automatically goes through the network, and you can have a multi-level maintenance involving maybe a help desk with a technical assistance center, maybe field support engineers, and then the design engineers, who's a multi-level hierarchy. And all the information could be stored, both the past, present, and the future, and that can be used for maturation and the future designs. Okay, so what I want to do in the next couple of slides is show you why hybrid models may be a better way to go, number one. And number two is, what if I don't have models? Can I just use data? Yes, you can. And I also said that the graphical models can include non-traditional information. For example, maybe audio, or we had a situation where whenever a Sikorsky helicopter was going through a wash, that is just like going through a car wash, then the turbine temperature used to spike up. Some intermittent falls used to happen. So those kinds of expert knowledge can be incorporated into these so-called graphical models, which I will be talking about later. Okay, so nowadays there is the whole issue of IoT. The question is, where do you want to put, what happened here? Oh, where do you want to put your network? Well, if you have a system and then you transmit all the data to a cloud, and that would be called a remote data acquisition. You're just acquiring the data from all these different systems that you've fielded, And then you're going to make the decision which one is good, which one is bad, and so on and so forth. The second place where you can put is hey, I don't want to be sending all the raw data. Maybe I will do some process data, which is I'm only going to send some indicators of failure. Those are the residuals I could be sending to the cloud. So in which case, all this part is going to be part of the system. On the other hand, I could even be making anomaly detections in the system. So in which case, all this part will be part of the system, and only I'm going to send the error codes. So you can see that the bandwidth requirements to send from the system to the network are going to decrease as I go in this direction. You can also have this case where I make all my diagnostic decisions right in the system, in which case all this part is going to be part of the system. Or in some cases, you may want to put onboard prognosis. This is not really done that often, but most of the time, onboard prognosis is done across a fleet of systems, like a fleet of automobiles, fleet of aircraft, and that typically tends to be done in the cloud. Okay, so that's basically how you could bring in the network into this SHM designs. So how you design which your architecture will depend upon where you're going to put the network. Okay, so why do I think that the hybrid models are good? This is an example of a CNC milling machine that my colleagues in the institute and I have been working on. And here what we do is we use a physics-based model. Looks like there's a problem with this. So a physics-based model was built and verified with something called VeriCut, and also with the actual data. So here it takes a set of inputs like the material, diameter, and the number of teeth, the machine setting conditions, like the cutting speed, spindle speed, depth of cut, width of cut, and the cut type, whether it's a face milling or the other kind of milling, and also the kind of workpiece that you're working on. And there are a set of models for power consumption, force components, torque, cutting fluid utilization, scrap generation, the temperature, and you've got a set of sensors that measure all these things: power consumption, cutting force, torque, scrap generation, so on and so forth. Okay, so one of the things that you will find very quickly is that these models, as George Box told a long time back, that all models are wrong and some models are useful. So you will see that when you get the experimental measurements, the physics-based models are not going to be representative. Physics-based models are not going to be representative of what happens in the real world. So that means you're going to get differences between the model predictions and the actual experiments. So what you can do is you can do something like what people have been doing in numerical analysis for a long time. Those are the iterative improvement. So we do a least squares and then use the residuals back again in the least squares to improve the solution. And in the context of machine learning, those people call them as gradient boosting, because gradients are nothing but negatives of the residuals. So you can use the residuals from experimental measurements of a healthy machine, and you could use that and the machine settings to build an incremental machine learning model. Now you get predictions from the physics-based model and your data-driven model, and together that is going to be your hybrid model predictions. And you can see here clearly that this was a physics-based model, is the blue one, and the hybrid model is a lot better in terms of representing the system, and this is the actual experiment. So still there are some differences, but hybrid models are better in terms of the mean square error predictions. And the nice thing about it is that you don't get false alarms. So when you have a bad model, you're going to get false alarms. That means even though the machine is operating okay, you will think that it's actually faulty. And also it also improves your detection probability as well. Just one second. All right, so this is the process that we went through is, hey, what is the most important machine setting? And you could actually rank order those things using dynamic programming. And it turns out that the depth of cut, width of cut, feed rate, and the spindle speed are the ranking. And the metric that you could use is, for example, the Kullback-Leibler divergence, which is essentially the distance between two probability distributions. So you got a healthy distribution of how your measurement should be behaving, and one with the toolware. And that difference can be used in a dynamic programming algorithm to rank other things. And you can see that you probably need all the 4 settings, and you can get as much as maybe more than 90% accuracy in terms of the diagnostics. And also this Kullback-Leibler divergence is also related to the false alarms, if you go and read the sequential detection theory. So over here we use the page skew sum test, and it is very good at detecting, and you can actually get a accuracy of as much as more than 90% for toolware greater than 0.02 millimeters. And clearly the hybrid model actually works better than any of the physics-based model or the machine learning models alone. So that's one message that I want to give. The second message that I want to give is basically what happens if I don't have a model or I haven't built a model yet. So in this case, we had a Haas milling machine where we just had only data on the static forces. We had a dynamometer where we could get these rotating forces, currents, voltages, power, temperature, and so on and so forth. So here we did time and frequency domain analysis of the data. So you can get time domain metrics, FFTs, and wavelets. You essentially get some features. And then you can use some similar kind of techniques to rank order these features, and then use them in an anomaly detector, which could be just a PCA-based Q statistic and T2 statistic, or the Q sum. And you could do the diagnosis using any of the classifiers, and you could build a model for how the toolware changes as a function of the number of runs. In this case, we had 7 parts made, and each part was run 4 times. So we had a total of 28 runs. And what we found was that the Gaussian process regression was better than a linear model. Looks like I have a spelling error here. Oh, God. All right. Okay. So the next one was, what if I just have only data, and if I have a non-traditional type of information, such as audio and video. So in this case, we had so-called Gerber Paragon fabric cutter. These are the guys, in fact, this is a Connecticut company. And they make these fabric cutters. They operate at 3,500 RPM. It's basically automatic cutting using a knife. And we wanted to check whether, just by listening to the machine, can you figure out whether you have a healthy machine? Sometimes these knives are not tightened, so maybe there's a loose knife. And what if sometimes people don't put the knife at all? Sometimes knife is there, but there's the belt that operates the knife is not attached to the knife. So can we figure out from the audio that you hear? For example, this is the case. For example, that's one of the cases. And this is the case. We had no knife and no belt, and we were able to basically distinguish what machine settings it was. In fact, we used the same idea for the Mazak CNC milling machine also, where we used the audio, and we're able to figure out at what was the depth of cut, cutting width of cut, and so on and so forth. The machine settings could also be figured out. And we also use the audio even for prognostics as well. So what it means is that there may be modeling technology where you could actually bring in different kinds of things, physics-based, data-driven, and non-traditional things into a single framework. And that's basically what we have developed over the years. So how would you go about designing SHM? Well, the first thing that you need to do is model how the faults are going to propagate to their manifestations. So it's essentially cause-effect type models. Causes are the faults and the effects are the observables. And then you'll essentially optimize the sensor suite. And of course, this is an iterative process because it's like a chicken egg problem. You have a sensor, and that sensor may have certain accuracy and certain cost and so on and so forth. And then when I take those measurements and design a statistical test, I'll get some false alarms and misdetections. And I would like to evaluate how efficacious those tests are. And you also don't want to be using too many redundant tests and should be adding more tests. In other words, maybe I may want to combine information from multiple tests and design one combined test. For example, maybe a classifier of some kind. Then the issue of identification or the diagnosis. Then the prediction. So the prediction should be always in terms of the health management of your system, not just trying to find what my residual useful life and based on the physics-based model. And when you go take it to the real life, they never work. Okay, a lot of people have tried to do that with gearboxes. They don't really work unless you adapt them with the data. So the key things that you want to know is, hey, how much time do I have before I need to start taking actions? Those are basically time to alarm. And also how much time do I have to intervention or time to maintenance. Then using that information, you essentially now you can see what the impact of the current situation in the future. For example, the NASA missions would like to know what is the impact of the current status on the future mission phases over the next day or two, and use those to replan and recover from any anomalies. So that involves essentially respond, recover, reconfigure, rectify, and repair. And of course, no model is going to be perfect. So you need to continuously be adapting, updating your models for novel faults. These are the so-called unanticipated faults where you find new relationships that you didn't even know existed. Okay, so this is basically the 7-step process that we advocate. So we believe that this modeling this fault to error characteristics. Oh, I'm sorry, there was some questions. Should I be answering the questions now or at the end?
No, please go ahead. At the end, we'll be having this question and answer.
Okay, sure. All right, so what is this multifunctional causal modeling that I've been talking about? Well, it's essentially you have a schematic of a system, which you know how it's connected. And then you could impose different components associated with those, and then the failure modes associated with those. So you can actually have a big system, subsystems, sub-subsystems, components, all the way at the lowest level, you have a failure mode. In fact, you can have any number of levels. So it's essentially a hierarchical description of your complex systems. So it captures the modules, interconnections, and the hierarchy in a directed graphical model. It adds failure modes and affected functions. And then it adds monitoring points. Those are the kinds of things that we designed using those physics-based models or the data-driven models or observations. And then you can do something called reachability analysis on this graph to see which causes manifest themselves as the effects. And the nice thing about these graphical models is that you can actually include quite a few interesting things that are of significance for military systems and the space systems. You will never send a system without redundancy into space. So you can have so-called AND nodes to model the redundancy, and that redundancy can be of different types. You could have analytic redundancy, information redundancy, physical redundancy, maybe multiple sensors measuring the same things. Or it could also be the logical redundancy. And no system, even a very simple engine or even a pump, is a single mode system. There may be multiple modes. For example, maybe valves at different open and close type situations. So switch nodes are the things that you can add to this graphical model to model the system modes and the mission phases. And you can have different types of faults, different degradation levels, for example. So we call them the general and the functional failures. General is a complete failure, and functional failures could be of different degradations. And you can have the faults don't manifest, especially mechanical things. It takes some time for fluid to flow through the system or the heat to flow through pipes. So the fault propagation delays, and the sensors will have their delays, and the system may be operated in different phases, and some systems may be turned off and on. And of course, you can get a lot of these models automatically through CAE interfaces. And the nice thing about these causal models is they enable you to traverse the so-called the ladder of causation. So what does it mean? It essentially implies that you could do something called the sensing, which is the lowest level. That's like a root cause analysis. The second thing is intervention. This is the thing that Julia Pearl talks about, the 3 layers of causation. The intervention is what if, given the current situation, what if I were to redistribute my power system load among the various loads in space? So you could see what the impact is going to be on the various things that you want to do in the future. So that's the intervention. And you can also do something called counterfactuals. Hey, what if I had done differently than the activities that I undertook the last time? So you could actually have a retrospective type analysis also with these kind of models. And also these are explainable models. We have had people, even pilots, able to explain how the faults are propagating through these kinds of systems. And NASA actually uses them for the Space Launch System as well as Ares. And now with this so-called Artemis program for the mission to Moon that's happening in the next couple of years. So Qualtech is the only company that was selected last year for this system health management. So Somnath can talk a lot more about those. Okay, so since we have some research scholars, what are the fundamental problems that we need to solve here? So clearly one is sensor optimization. Second is test design. Third is, how do I do onboard diagnosis? And guided troubleshooting. Can I minimize the time to troubleshoot things? And of course, the predictive maintenance. So in terms of the sensor optimization, the problem is going to be to find the most informative sensors. I sort of gave you dynamic programming and mutual information-based things, but actually this is a very interesting problem that we have addressed in lots of different ways. In fact, George Bolas, who I work with, also has done this kind of work for the 787. Most informative sensors that minimize the test or sensor cost subject to constraints on the fault detection, fault isolation. We have papers using genetic algorithm, Lagrangian relaxation, approximate dynamic programming. Then a lot of people spend, especially the signal detection people, a lot of the people in control theory using model-based anomaly detection, so-called residual-based, using Kalman filters, particle filters and things like that, and statistical classifiers. And of course, the machine learning people using autoencoders, LSTM, and deep learning type techniques. So the key idea here is the tests need to adapt to the context in which the system is operating. So you need to have adaptive thresholds that are robust to uncertainty in your model, and also that adapt to different system configurations. Okay, so then there is the issue of real-time diagnostics. So this is the issue of inferring multiple couple and intermittent faults with fault propagation and observation delays. So we could represent this using, for example, factorial hidden Markov models or coupled hidden Markov models or even dynamic Bayesian networks. And depending upon how you formulate it, it becomes a nice set covering type problems. So something called delay dynamic set covering, if it's a dynamic thing. And also you could use for factorial hidden Markov or coupled models using Lagrangian relaxation and Viterbi decoding type algorithms. So the guided troubleshooting is how I started this whole research way back in '84. And how do you determine optimal test sequence? It's sort of like an adaptive troubleshooting. That means depending upon the current state, you take your next action, sort of like the MDP. So state action type of decisions. And even those days, now it's become very popular with all these AlphaGo and things like that. So we had essentially developed approximate dynamic programming techniques with variable search and depth and breadth type of search to make them actually practical using something called undocked graph search and information theory. Then we couple them with rollout and sort of like a Monte Carlo search type techniques of approximate dynamic programming. And a nice thing about this particular problem is there's a technique based on mutual information that works very good most of the time. And only in those few cases where it doesn't, that's where rollout type of things can actually work. And of course, you could use reinforcement learning techniques for this also. And in terms of predictive maintenance, we've developed techniques based on moving horizon, interacting multiple models, machine learning, sort of like indicated one of those using Gaussian processes. And of course, you could use the same multifunctional model type approach where you infer what has gone wrong and then do the appropriate prognosis for that particular isolated component. And that's what is called inference-based prognosis. So there are a lot of interesting mathematical problems. I'll give you a whole 3 or 4 page references where you could pursue more of these. So we developed all these tools. Initially, we had developed these so-called graphical modeling tools using Teams. And then it led to NASA asking for, hey, can we build onboard diagnosis? That's where Teams real-time embedded diagnosis tool was developed. With the space station, they asked us to develop remote diagnostic server. And that can also be used for guided troubleshooting as well as cloud-based diagnosis that we can do, where you send all your error codes and it does the diagnosis there. And Teammate is essentially a guided troubleshooting for the technicians. And you can also do it using mobile devices. Okay, so how can you use these things? You could use these models for right at the design and conceptual phase to evaluate the safety, testability, and supportability analysis, because one of the nice things about these graphical models is that you don't have to have a separate model for fault trace anymore. You can actually do risk analysis, fault trace for any effect that you want, automatically built for you from these graphical models. And you can also do FEMICA, which is the failure modes, effects, and criticality analysis that comes out of this kind of models automatically. So you can do, for example, if it's an interconnected system, how do the faults propagate through subsystems? And you can optimize detection diagnosis of critical faults. So there are criticality level 1, 2, 3, 4. And you can optimize the fault isolation strategies. You can quantify what the costs are going to be right up front. Remember the graph that I had is in the conceptual phase itself, you would like to know what your costs of your systems are going to be. And of course, sensor placement optimization. And you could do smart diagnosis. In fact, the intelligent systems are supposed to do self-service. That means a seamless integration of the onboard, offboard. That means you don't need to redo all the work that was done before. So all the information gets basically transparently gets transmitted to the appropriate level of maintenance. So you can use it for health monitoring, remote diagnosis, and telediagnosis, and embedded diagnosis. And PHM, here the key things are going to be time to alarm and time to maintenance. And another reason why we actually split up that into data acquisition, then we do residual generation, then the tests, diagnosis, and prognosis is sort of like the way that we have the ISO for the internet, where you can have different technologies coming in. And that is extremely important because when you're building a very complicated system, you are going to get your different subsystems from different vendors. And those vendors may not want to share all the inner details of the subsystems. So by having this detection being done separately than diagnosis actually can be done generically, and it actually scales up quite well. But you can actually use domain-dependent residual generation and the test designs, and then you can actually combine them into a higher level, system level monitoring system. So at the system level, you would like to essentially, when am I going to get an alarm and how much time I have to maintain my system? And of course, guided troubleshooting, and make every technician perform like an expert. And I'll give you some indications that actually these things help. One of the things that you'll find very quickly is that the humans are local optimizers, whereas these MDP-based approaches actually can look at much broader breadth and depth and come up with better solutions. And of course, automatically you could be ordering parts and essentially have the right parts at the right time. Okay, so how do you integrate models from different things? So this is how we, you could basically have all these SysML, or maybe there's a FEMICA that's already built for you. You may have schematics. You may have CAD CAE type of systems. For example, MATLAB, you can do fault simulations, and those things may be already available to you. You could actually integrate all those into our multifunctional models, and out comes all these fault trays. You can select any effect and automatically generate the fault trays. And of course, the FEMICA reports also can come. We can do sorts of trade studies, risk assessment studies, and lots of different metrics that come out of these kinds of models. One application of that was in the context of automated manufacturing facility at Warner Robins that Qualtech did. What they did was essentially automatically build an electroplating process that involved like 50 different recipes for coating aircraft parts. So what you have here is equipment schematics that can be automatically gotten into the model. And also you may have a model library and different recipes for electrochemical plating. So those recipes may be in the form of Excel sheets. Those are converted into XML. And then they automatically generate by taking, for this particular recipe, these are the equipment that are involved, and this happens to be the model for that particular chemical process recipe. And then you can generate for that particular chemical plating process, you can generate the so-called process FEMICA as well as the equipment FEMICA that's involved. And this all can be done automatically. And you may also have a lot of error codes. Those can be incorporated into Teams model, and is also used for troubleshooting. So this is sort of like one application of how different data from different engineering domains can be brought into a single graphical model. And they can do it for 50 metal finishing recipes. So some of our applications have been in the automotive. For example, with the General Motors and Toyota. Toyota right now, we're working with some power electronic devices. In the aerospace, we work with Pratt and as well as Sikorsky on the engines. And NASA, primarily in orbital maneuvering systems, rockets, and the so-called Optimus. And habitats, we're part of a big center where Purdue is leading UConn and Harvard. UConn is involved in the situational awareness aspects of it. And guided troubleshooting has been used in medical equipment as well as the military vehicles and semiconductor and power systems and buildings with HVAC and power quality monitoring for General Electric. Okay, so let me briefly go through 3 examples. One about onboard diagnosis, one on guided troubleshooting, actually 2 on guided troubleshooting, and then conclude. Okay, so what is the simplest reasoning that you can have, not including all these dynamics and probabilistic transitions and things like that. So the diagnostic reasoning essentially works like this. Suppose error code 1 is caused by, say, A through A, C, D, E, F, G, H, and I. 2 is caused by this, and 3 may be caused by those components, and 4 caused by those. So think of it almost like you are a classifier where some subset of the components are in one, say, class 0, and the other subsets are in class 1. So these are the ones. When you get a 1, that means error code becomes 1. That means you say this class 1. Those are the things that you're going to suspect. And this is the scenario that you have. Error codes 1 and 2 are detected. That means 1 and 2 happen, but you don't see 3 and 4. So what do you think could have caused the problem? So clearly, the things that are common to 1 and 2 are C, D, and E. So those you should suspect. And since 4 hasn't occurred, so C, D should be removed, and E is the one that is the problem. So you could do diagnosis like that. But this is a too simplistic thing, but actually there are lots of interesting things happen. What if I have multiple faults? The thing that I said can handle that. What if I have multiple modes of system operation? What it means is that your graph itself changes as I vary from one system mode to another system mode. And what if I have probabilistic outcomes, namely false alarms and misdetections? What if I have a confusion matrix associated with my classifier? What if I have delays due to sensors and this was a failure propagation effects? So all those complicate the problem, but you could mathematically solve those. So this is an example where we compared a legacy Pratt & Whitney engine diagnostics with our solution. And one of the things that we found is that by using this, both the pass and the fail, we could actually improve the diagnostic accuracy significantly and also reduce the false alarms. So this was the actual engine test data, about 12,000 different test cases that they ran. Okay, in terms of the test sequencing, some blind trials were done by 2 semiconductor companies. For example, in the first case, expert took about 15 minutes. Non-expert with our diagnostic server also took 15 minutes. There's one case, actually, our system beat the expert. But non-expert without the tool was essentially gave up, or they didn't know what the heck to do. And there was a second experiment that was also done by another company, KLA Tenko, I think. And this is expert without Teams took 7 hours and 27 minutes. Novice took only about 24 minutes. Novice without took 8 hours and 24 minutes and things like that. So consistently what you find is that because these things can look ahead further and also bet, they typically, you can save as much as 75 to 90% in troubleshooting time across a range of applications. So this is an example of how you could have this multi-HLN maintenance, where you have got a customer that calls, sends something to a call center, and call center uses that information by the technical assistance center people. Those are basically some engineers. They can isolate the problem to a few things, and then they can dispatch the technicians appropriately, either through Teammate or the Pack and Go, and all that information automatically comes back into the cloud. Okay, so this is how we could actually implement, and a company called SciX, which is a Canadian company that makes this, mass spectrograph instruments actually implemented this idea. And they're also going to put it right in the machine using the TeamsRT. Okay, so this is the last slide. So how do you get prognostic into the thing? So let me illustrate what I mean by the time to alarm and time to maintenance. So if you do the early detection, so detectable degradation, where things start going degrading, so that could be sort of like on the verge of between green and yellow. And this is the time when your test will actually, error code will come on. So this is how much time that you have to alarm, time to alarm. So you can start planning what you should be doing if it reaches this particular state. So even if the alarm comes, you may still have time before the thing actually conks out. So this is basically the window of opportunity for preventive maintenance. So by having this time to alarm and time to maintenance, you could do essentially health management of your system rather than just compute this residual useful life that nobody looks at. It is important to have this kind of time when this particular test is going to give an error code and how much time that you have to fix things. All right. And of course, this is reactive maintenance, is when the failure happens, then you're stuck. And we have applied this to KMAX is essentially an automated helicopter. And of course, F-18 actuators. There's a company called Moog that makes these actuators. And we're using this to Toyota power modules and suspension systems. As you can see a paper that we have done on how prognostic should be done, and also medical devices. All right. Another nice thing about this having this system health management digital twins is you can use them to train your technicians. So you can, for example, you can have a digital twin, and that can generate most difficult failure scenarios. And those training scenarios could be aided by, say, Teams RDS with augmented reality or VR-enabled maintenance training. And all that information is collected, and you could use there's some really interesting psychology stuff. Learning sciences enables scoring, like how well these people are doing, those performance metrics, and those could be used by the instructor to decide on what, how to evaluate the technicians and what kind of training they need. So you can have sort of like a closed loop decision support for training assessment. Okay, with all that, I would like to caution that you need to beware of models and machine learning that is done without domain knowledge. All the things that AI people claim, you need to be taking it with a grain of salt. As President Reagan used to say about Russians, trust but verify. So you need to trust but verify how well these machine learning things work. And of course, the human greed is one of the things that you need to watch out for. So clearly, inaccurate models lead to inaccurate conclusions. This is in a different applications where we are trying to use CFD simulations to have a machine learning model to do both adaptive sampling as well as simplified models. And one of the things that we find is that these models themselves, they don't converge, and there are lots of issues. So you need to be having some domain knowledge, whether you can trust the results that come out of those models. This is another case where we work with probably the best weather forecasters that we have in the United States Navy. In Monterey, there's a naval research lab. And we tried using the machine learning to predict where the clouds are going to be, or what kind of clouds you'll have at a particular location. And it turns out that there are 5 or 6 different clouds. In fact, these people are such experts of classifying these clouds. And once we started using their expertise into our machine learning models, we started getting better cloud predictions. For example, what happened here? we were able to increase the accuracy significantly. This is just machine learning. This is the physics-based unstable clouds. ETS is sort of like it's called equitable threat score that has been there since actually 1884 by the weather forecasters. And if you get something above 0.35 is good. So we were able to increase it significantly, 0.56. And the Cohen's kappa was increased from both of these, either physics-based or the machine learning, to 0.72. And of course, you should always watch out for the human factors. And these are the examples that we already talked about right at the beginning, with trying to save a penny and spend thousands of dollars. Okay, I think one of the key unsolved problems is how do you automatically update these models for unanticipated faults? So that's an area. We've done a little bit of work on the HVAC. We published some papers, but that is an unsolved problem. Online adaptive inferencing, basically learning these causal models online, and learning the system parameters and models online from text, speech, and image data. This is the non-traditional data sources. Smart machines, remote diagnostics, and telemaintenance architectures, like where do you put your cloud? Where do you put your network? Applications of these to real-world systems, and doing the opportunistic maintenance. For example, you may have an opportunity to fix it because the customer came to the dealership. So, hey, you're going to have a problem in the next 2 weeks, might as well fix it now. And links to automatic supply chain management processes, those are called autonomic logistics. Okay. I came from a very small village of maybe 562 people, and we didn't even have electricity till 73. And both my parents were not educated. So IIT KGP actually made my life. And I've learned quite a few things. I was at the right place at the right time, I believe. And one of the things that I recommend to all the research scholars and undergrad students is keep the inquisitiveness alive. Always be learning from anybody or anything every day. And you need to have attention to details. So, for example, when you make a presentation, make sure that you basically revise and revise and revise till you're happy with it. Link up with people with high expectations. That was one good thing for me is I did not know who my advisor was. My advisor happened to be a top optimal control guy that had graduated from MIT, and that gave me a lot of connections with really people with high expectations, and that helped me a lot in terms of, and also my colleague happens to be Jakob Barcelom. He's very, a guy that with very high expectations. So you tend to, there is an osmosis that goes through. Hard work always pays off. And this is something that I see with a lot of my students nowadays with all these MATLAB and Python, things like that. They tend to be very sloppy in terms of programming. And when we were writing the code for all these teams and all that stuff, we make sure that every line, do you need it? So every bit of efficiency from the code, we try and squeeze. Write, revise, write, especially when you're writing papers. You want to have your advisor tell you that you're an idiot rather than somebody from a reviewer telling you that. So I'm sure that your teachers already tell you that. And take care of the people that give you money, they'll take care of you. And that has been the case for me. And do what interests you the most. For example, my kids didn't want to go into engineering, but I told them, whatever you do, be the best you want to be. And finances will take care of you. If you have all these things, you will do well in life. And when learning a subject, get multiple viewpoints. So one of the things, although my father was not educated, but he had a lot of friends who were educated. So he used to basically buy books for us that were being used in towns and things like that. And that actually enabled me to look at the problem from multiple viewpoints. And that's what I do. I never use a book for teaching. And I essentially get all the information and make my own lecture notes, and that actually works out very good for you. And strive for clarity and understanding fundamentals and the papers. So quite often what happens is that when students read papers, they think that, oh, this came from this particular university, There also happens to be humans, by the way. So you strive for clarity, understanding fundamentals in the paper. So once you understand that, you'll see that that actually will help you a lot in doing your research. And this is my policy in terms of my students. I take care of them before I take care of myself, because unlike in India, we have to get the money from sponsors, and the sponsorship is what supports these students. So you want to take care of your students and the people that work for you before you take care of yourself. So those are the life's lessons that I wanted to impart. And these are the set of papers. I can send this presentation to if you want to put it up. And you can learn a lot more about mathematics from these. Okay, with that, I can stop sharing and answer any questions. So let's go to chat. So do you want to moderate, Dr. Paul?
Yeah. So, the Professor Krishna Pattipati, it's really wonderful that you have given a nice description about the digital twin, various aspects of the digital twin. You have given us the examples of the hybrid, the model. You have also told that, how the data-driven model from the audio, they can be created. You have given us the integration of the multi-source model, which is a very nice thing, graphical representations of that, and some of the use cases, and the research areas that you have mentioned is really wonderful. I mean, those are the most relevant as far as today's manufacturing is concerned.
Yeah, especially if you want to build resilient systems, you are going to get unanticipated things you didn't anticipate. So you need to be able to adapt. And essentially, I see there are three ways to do resilient systems. One is build it robust.
Yeah.
The second is you adapt as you learn with observations. And the third thing is you need to be able to identify what your new model is and act on it. So the last one, we call them agile response to resilient or resilient systems. So agility and adaptivity are the key things for intelligent systems. Okay.
So there are some questions, in the chat box. I just
do you get any help in repeating the experiments?
Yeah.
On the
one of the questions
manufacturing, we have Connecticut is a very good state because we are supposed to be a manufacturing state. So we have something called CCAT, Center for Advanced Technology, Connecticut Center for Advanced Technology. So these people run the experiments for us and give us the data. Yes. And that's how we got the data. Okay, use Taguchi orthogonal arrays for quick identification of key sensors. Yeah, you could do that. In fact, you can do better than the Taguchi by using something called adaptive sampling. So essentially, if you compute the mutual information between what you know so far to what you might measure, there's a very nice expression that you get in terms of the covariance matrix, and you can basically optimize with respect to that. And you can do better than some of these orthogonal array type of things. I would be delighted to. So you're at Oklahoma University? I think I met somebody from there. I visit Indian Institute of Science. See, I come from South, so that's the reason why I have not made up to IIT Kharagpur. Although IIT Kharagpur, a lot of my friends at the time, they helped me a lot with respect to my passport and getting my tickets and so on and so forth from Calcutta. And it turns out that my at least one prominent student, Somnath Deb, who's actually in India right now. He is another guy that I strongly recommend getting, and he can give a lot better talk than I can, especially in this particular area. He's a lot more experience. Yeah, I would love to have interaction. Prognosis is regarded as net cost, how the cost saving can be quantified due to PHM in industrial level. Well, the reason why the PHM is sort of like getting the bad name is a lot of the people are just focused on that so-called residual useful life and coming up with these esoteric models. And when you actually apply them to the real world data, they're not working as well. Whereas it is a lot easier to estimate, for example, hey, how much time I have before my test is going to give me an alarm, or how much time I have for maintenance. Those kinds of red, green, yellow type of coloring scheme is a lot better, because that's all a person that is maintaining the system will need. So if you focus not from the prognostics, residual useful life, to health management, system health management, I think you'll have a lot better success. In fact, that's how I think Delta is having some success in that area. How we go ahead with diagnostic, prognostic, and battery pack management, which is essential for electric vehicles. Okay, I got that's a whole different area that I've been involved. Because of the Toyota work, we had developed some, and there was something called a Freedom Car in the 90s. So Idaho National Lab had data, and we had developed the impedance spectroscopy based techniques for getting a battery model and using it for residual, basically prognostic type of things, both state of charge and state of health. And then based on that work, actually, Fairchild came to us and said, hey, can you guys build us SOC/SOH for mobile devices? So if you go and take a look at some of the literature, we've published quite a bit on that for SOC, and even doing the open circuit voltage characterization, and also doing the battery health management and the different temperatures. And right now I'm actually working with a postdoc of mine that worked with me on that. He's at the University of Windsor, Balakumar Balasingam. So there are quite a few papers that we have done on this battery pack management. So you essentially need to have adaptive models for the batteries, using say particle filters or external Kalman filters for SOC estimation, and keeping track of the online estimation of the capacity and resistance, which are characteristics of capacity fade and power fade, and using those to estimate how much time that you have for the battery. So we have done some work on that stuff, yeah. The next question, can you mention any application methodology in silicon other than the KLX? Okay, yeah, there was a company called Arbotech in Israel. They used our tool for guided troubleshooting, and KLA10 Core is another one. And right now, I think most of our stuff is in NASA and petrol boats for the Navy, and some missile systems for Raytheon and some other companies. So Somnath can tell you a lot more, because he's the one that runs the company every day. What is your experience with online teaching these days? That's a very good question. Well, I had to teach last spring, starting from March till May. That did not go as well as the fall. Fall, it went extremely well. So what I did in the fall was I had both synchronous and asynchronous teaching. So I taught a digital control course. So I recorded all the videos, maybe like a 60 videos for the course. So the students could watch those and come to the class. And I essentially had a flipped class. Basically, we were doing problem solving, answering questions and things like that in the synchronous class. And also had a synchronous office hours. And the way that I do that particular course is not only just the lectures, but also we have these projects. So the students actually have to make, do a 3-phase project. The first phase is sort of like how they're going to design the control system. So modeling and conceptual designs type of thing. And they have to make presentations. Then they do all the classical designs, and then they do the so-called modern state space design. So there's a lot of interaction with the students, and that went extremely well. In fact, I got accolades from the provost and all that for that particular thing. So that model seems to work very well. And I use the same thing for my machine learning, advanced machine learning course that I teach in the spring semester. That's a graduate course. And we had a very similar kind of feedback. All right.
How to realize the operation of multiphysics model in real time for a digital twin application?
Yeah, this I don't know. Because one of the things that we are finding that for very large scale systems, like spacecraft or habitat, so we built, as part of the Purdue, UConn, Harvard experience, we built a model that integrated the power systems, it integrated the structures, it integrated thermal systems, it integrated all this robotic type of things into overall MCVT. And one of the things that we found is that even if you wanted to simulate 30 seconds of the thing, it was taking a significant amount of time. So I'm not sure whether these multi-physics models can be used in real time right now, although hopefully quantum computing and all might, maybe 20, 30 years from now, if that becomes reality. Right now, what you want to do is take these multi-physics models and develop something called gray box models. Gray box models are essentially, they use physics, but that physics is simplified physics. And that means it will know all the inputs and the outputs, but the dynamics may not be as complicated. So it will give you some approximate response of the system, which can be the discrepancies between the actual physics-based model and the gray box model can be fixed with a data-driven component and use that hybrid model for real-time applications. So that's how I see the current application of this. Of course, you need to use GPUs and things like that if you want to make this multi-physics models work. So if you go to take a look at that chapter that I wrote with Ken Ross, you'll see that GPUs are mentioned quite a lot. And that's what actually is making it feasible to do, go from the concept to the detailed design and engineering development. So that's where the applications are. But use those to develop the so-called gray box models that can be used in real time. How can we predict programs where there is lack of knowledge, information, data of the system? Yes, this is where these multi-physics models can be quite useful, because now we have maybe an approximate physics-based model that you can use to do all your fault simulations. That's exactly the way that we did with the resilient habitats, where we said, hey, if a meteorite struck, so it impacted the structures, then there was dust on the nuclear and the solar power sources, and the batteries had to take over, and batteries told this human robot teams that they got maybe 8 hours to fix things. So they could only fix, say, for example, the solar arrays, clean up the dust, and the nuclear, because it happened to have in the dormant stage, where now the astronauts have to come whenever they come to fix the nuclear source. So till then, what do? You change your system operating with the minimal loads. So that's the kind of resilience that you want to build. So you can use basically this kind of physics-based models. And as you start getting the data, you can update those models. So that's what that loop was there, adaptation model of the models. Okay.
Professor, you mentioned about your book on the digital twin. When it
That's not my book. I just wrote one chapter in it.
Okay. So when it will be coming up?
Yeah, it's coming here in 2021 spring. If you want, I can send that paper. That's ready. I can send my version of the thing. Okay, Ken Rosen is the guy. Yeah.
So it is really
it's a non-mathematical stuff, how it should be done. It's more of a, how do you operate in an enterprise?
Yeah, so it's more of the framework development of the system.
Right. Like what are the issues that you need to be considering, and
yeah.
Yeah.
Okay, and does it talk about any of the use cases that you have mentioned?
Some use cases, yeah. In fact, yeah, I can maybe show it to you guys.
It's fine. We can also see it later on. Yeah.
Yeah. Digital twin. See, this is a 48th version of our things. Let me share this. Oh, okay. I don't have sharing facility, so.
Oh. Yeah, we'll check it from the screen, because
sure.
This is one of the.
I'll send you a copy of that chapter.
Yeah. That will be very nice.
Sure. But yeah, if you want, I can put you in touch with this guy, but the editor Ed Graybot is a good guy to know.
Yeah.
So he used to work for a company called SAIC, and so he was involved in lots of interesting work, and he could be a very good person on the digital twins. He gave a talk on the West Coast, I think, a couple of months back. So he had very good overview of how digital twins is supposed to work.
It would be great if we just get
connected.
Yeah, that would be wonderful. So it was a very nice, the presentation, and you have thoroughly explained about the digital twin, its application, various applications. We learned a lot, and we'll be in touch with you because this is one of the areas where the lot of faculty members are working from the Center of Excellence. We are working, very seriously in this aspect. So we'll be in touch with you and take your help.
Right.
Yeah.
So did you know Sarit Das? Sarit Das was my classmate, actually. He was the EE professor, I think. He just retired a couple of years back.
Professor Sarit Das is
Sarit Das. Yeah, Sarit was my classmate in 75, and then he was a faculty member in the electrical engineering, I think, and he was department head also.
Yes, he did. Yeah.
Okay.
I think 3-4 years back.
Yeah, he retired, and I think he lives in Hyderabad now. Yeah. Right.
Okay. Professor Sarit Das is your classmate.
Yes.
Oh, good.
So we used to call him Big Daddy at the time. So.
Okay. Thank you so much. Thank you. You are grateful for your, the talk and presence, and we'll be in touch with you and take your help so that our Center of Excellence, the books are.
Yeah, I'll be glad to help out in any way I can. Yeah. Thanks.
So yeah. So again, the audience next week, that will be, I think, 3rd of July. Yeah. So they are the speakers in the month of July.
Yeah,
3rd of July would be Santosh Devasiya. So Santosh Devasiya will be talking about the multi-robot task allocation. Then we have got a speaker from the industry Tata Sons, Dr. Purnendu Sinha would be talking about the tourism, government, and academia. So how the ecosystems can be developed, which is a very much required as far as today's the manufacturing research is concerned. The presence of industry and academia working together. And I think we have already packed up for till September, I think we are already the book. And Professor Amitabh Dey would be on additive manufacturing from IIT Bombay on July 17th. Then we are going to have a speaker from our own institute, Professor Sudeshna Sarkar. Professor Sarkar will be talking about the AI and its activity in manufacturing. And then Professor Paulo from University of Manchester on the additive manufacturing. So with these 5 speakers, we'll be finishing the month of July, and then August, September, all are getting scheduled. Thank you so much.